Welcome to Complexity Made Simple. My name is Paul Allen, and before we get on to today's video, just a reminder of how you can support the channel. Please subscribe, please leave comments on all the videos because that really does help. But if you want to support the channel further, there is a donation page. Please go to Buy Me a Coffee and leave a donation, which is always fantastically helpful. Keeps the channel moving and allows me to make all of this fresh material. But if you want a textbook that contains all the good stuff from the videos, please click on the link and buy, drink tea and read the paper from lulu.com. All of these things really help the channel. Thank you to all the people that continue to buy this textbook. It really is fantastically helpful. Now let's get on to today's video. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's newsletter is a case study, another case study, and this case study is again on a similar line to recent videos. This is all about CPK. This is all about improving your process capability. And when I talk about this, so this is about process capability. We're going to see a case study looking at CPK. What we're talking about is removing chaos from your process capability. So the particular pattern that you're going to see in your process capability is a process capability that looks like this. And what you're trying to do, of course, is squeeze that shape in. That's what we're going to take a look at. Now, if you were looking at that on a graph, of course, the graph would typically look like this. If these are your tolerances, you'd see this chaotic swinging from top to bottom. It's neither above the tolerance nor below the tolerance. It's just doing everything. And what you're trying to do is make your process behave inside those specification limits. And what you're going to see is exactly this pattern in the case study, and you're going to see the guy do some very straightforward things, not necessarily easy. This is hard work, 2-3 months work to do this, but actually it's very straightforward to just squeeze all this in and get process control. So let's take a look at the case study. Okay, so here we are. It's a straightforward grinding machine. You can see we have a picture here of this machine. I'm guessing the machine is the thick end of 40 years old. You know, the kind of thing where people say, oh, we can't do any better than this, and they kind of give up even before they start. Well, what you're going to see here is with some very straightforward approaches to your process. You can make any process do this, and it's about being detailed. The person is going to get very detailed with his process analysis. He's not going to look for one root cause, because there isn't one root cause in this type of problem. So let's look at what he's aiming to do. So he's got this track diameter grinding process, and the definition he's given it is that it's unstable. You'll see from the graph in a moment why he's using that particular phrase, but he has a current defect rate of 10%. I would probably say, when we look at this, it's probably worse than that. And he wants to get it down to 1%, which, you know, it's a 90% reduction in his defect rate. My view probably is that's probably not ambitious enough, but we'll take a look. I think he does better than 1% when he gets to the end of this particular project. So here is the current performance. So here's the graph I've just drawn on the board. Yeah. So here's the idea of chaos. You know, the process is going above and below the tolerance, swinging around wildly. Now this graph is 40 consecutive parts but it does involve, look, the dressing cycle every 10 parts. So that variable is in this graph. But this really is as good as this process can ever be. Now really, the theoretical definition, you know, we're going to call this CPK, but actually what people often call this, they call it CMK. M standing for machine, because this is as good as the machine can do, with pretty much every other variable stripped out of the performance. So in theory this is CMK. His CPK is probably worse than this. Once the operator starts to get panicked by these results here that get close to the tolerance and starts adjusting the process and other variables kick in, it'll probably be a lot worse than this. But it's 40 consecutive, and this is a great thing to do. 40 consecutive, hands off, except for the dressing process. Take a look at the histogram, because of course what we're trying to just ascertain is how normal are we. Well, there's a little bit of data missing from the tails here, so and that's not unusual when you've got a chaotic process. So it's normal-ish, but you know, not brilliantly normal. And then of course he does his CPK diagram, and the CPK diagram is giving him that 10%, and that's what he's saying is the current performance. But that 10% is from the 40 consecutive. Yeah, so there's a good chance that this 10% is worse than that. All right, so there's his current performance. Now the technique he's going to use here is very simple. He's going to go process flow, cause and effect, and he's going to identify variables. Another word for variables, they are inputs to the process. If you allow inputs to move, you get variability. In other words, you will make this distribution wider. If you fix variables, then you will make the distribution narrower, and you will improve your capability and remove the chaos. So what he's going to do, he's going to go process flow, cause and effect. He's going to find in a very detailed way all the inputs. Now when I talk about all the inputs, I would call this a high fidelity way of looking at your process. Poor see 5S is in there, because sometimes 5S helps you fix this particular problem. So he's made a plan. This is his plan of action to get his ends under control. So let's have a look what he does. So simple look, and this people would say this isn't Six Sigma, this is very lean. Yeah, it is very lean. I don't care how you get to high fidelity control of your process, whether you call it lean or Six Sigma, but you need to do this. So let's take a look. What's he done? Well, look, he's just drawn indicators around all the metal work, where the Allen key should be, so people know how to set this up. He's drawn around this block, look, so that you can just position it perfectly. What else have we got here? Yeah, so he's just showing you these things here, how they've been controlled effectively. He's put some other indicator lines, look, up there. Simple stuff really, isn't it? But you know, it takes time to do all of this type of work. What else have we got? Then he's spent a bit of time, look, creating a standard operating procedure. So let's look at this. Now this is all about maintenance, look. So here, what do we say? Let's have a look. Daily maintenance, look, carried out by the operator. Weekly maintenance carried out by the maintenance personnel. So, and by the way, a lot of your variability starts and finishes with maintenance. Oftentimes you buy yourself a new machine. The machine works great, well inside the tolerances, and then you allow the machine to deteriorate, and eventually it starts making defects. At that point, you start to panic. By the way, the other thing that happens is you sometimes expect the operator to get you out of this mess, and he starts swinging on the dials and making the process go up and down even more, making it worse. Maintenance is the start and the end of this process. So that's weekly. I think the next one is monthly, and he works his way through all of this. So all the maintenance now is documented daily, weekly, monthly, roles and responsibilities, whether the operator does it, whether the maintenance crew do it, etc. And it's nice and detailed. It's high fidelity. Part of this, he discovers this particular problem. Now this is a setup. Now this setup is not touched by anyone. This limit switch here works on a cam, so the cam is rotating on the back of the machine, and what the cam does is it changes the feed speed. So there is a rough feed and there is a finishing feed. Yeah, now clearly this can be nice and fast. This typically, the finish speed is slow. This would normally be fast. And this thing is supposed to do that. It was set up the wrong way round. So what they did was they roughed out, and of course this is the biggest cut. The roughing cut is the deep cut. They do that very, very slowly. And then the finishing cut was done very, very fast. So this cam and the limit switch was set up completely the wrong way around. And you can see here, look, he's got a cycle time. He got a cycle time which lasted 2 minutes, mainly because this thing was going slow instead of fast. But the cycle time was 2 minutes. He's now taken the cycle time down to 25 seconds. Okay, now people sometimes say to me, but you wouldn't make this mistake. Don't forget, you've got an operator standing in front of this machine who you pay minimum wages to. You give them minimum training. You just expect them to stand in front of the machine, load the parts and take the finished goods away all day, and occasionally do a few measurements. They have no clue how this machine works. That they've just been given a process that's got a cycle time of 2 minutes. I don't know what's supposed to happen. So people say, well, this wouldn't happen. Yes, this happens all the time. Yeah, bits of machinery set up wrong, speeds and feeds are inappropriate, etc. There's all kinds of problems like this because you are not high fidelity. You're not taking enough time and effort to check how your machines are set up, maintained and being run. So what's he done? Well, he's put some markings in place. He's put some standard operating procedures in place, and he's corrected this particular problem. So he sped up the process by 75%, which is incredible. Now then, let's take a look how the process works. So now he goes back to the machine and he does a capability study again. 40 consecutive, hands off. Just before he does that, just something I forgot. He's going to do an MSA. So he's doing a measurement system analysis. Now, if you look at the measurement system analysis, it actually doesn't pass the test. Less than 0.3 is acceptable. So, you know, greater than 0.3, which is what we've got there on precision to tolerance, precision to ratio, precision to total, that is a fail. So in theory, you should be sorting that out. However, when we looked at the information, operator 2, which are, you know, the results of operator 2 look are clearly different from the other two operators. This guy is the apprentice. So you can see that, yeah, he's not really up to the job of measuring at the moment. If we take those results out of this, then we get a good result. Okay, moving on. So now look, he does another 40 consecutive parts. Now look at the difference here. So there's the original performance, there's the new performance. Now something's happening here which is very different, by the way. He now has this run on the process, which is something he needs to sort out. But potentially this process could be defect free now. By the way, when you've got a run on the process like that, that will probably have a root cause. That's a single thing that's doing that. It's a setting of some kind. It's a little process that's going wrong and driving the process down. So of course he needs to sort that out. But for now, actually, that's a very easy process to control. Of course, every now and again, if the operator just swings the process up, then of course the process will run down a second time. So it'd be very easy to get this to a defect-free place. Very, very easy. However, what he's done, of course, is he's gone through the same analysis that he did before. So he took the previous data, and of course he did a histogram. That's the new data set, by the way. And then he does a CPK. And of course what he's saying to me, look, is that the CPK now is now giving him 8,196 defects per million, which of course is 0.8%. He's below his 1% target. So all good. Now what I said to him is, this probably isn't true. It's probably better than this. Whenever you're trying to decide, is my process normal? So when you're looking at this and you're asking the question, do I have normality or not? That's one of the questions you're just asking. You don't need to do tests for this, by the way. Just your common sense will do. Because normality is going to estimate what's going to happen. It's going to estimate your defect rate. So the question is that a good estimate of what's likely to happen? Well, no, because that pattern probably isn't present in the data set. The data set probably looks more like this. Look, we've got a smaller distribution which sits up, and then the distribution is gradually moving down. So if you look at the CPK diagram, it's probably more like this. Look, you've got a diagram that does this, and of course then you can swing it back. So probably this, is it a good estimate of what's going on? I personally don't think it is, but you know, is that a bad thing? No, because it's going to be better than what we originally planned. And there is a simple example of process flow. Cause and effect, NCX, SOP. What are you doing? You are looking at the process in a high fidelity, detailed way. That's what this guy did. It's very straightforward, but it still takes about 3 months to do this. This is not easy to do if you're not a high fidelity company, if it's not what you normally do. Okay, so this is going to take 3 months to achieve this, but think about it. Nothing was difficult in this case study. It just took a little bit of detail to do it. It just took the idea of inputs, control, outputs. Okay, so I hope you enjoyed that case study. Now I'm sure for some of you, you're going to say, yeah, but we don't get that problem. We already have that level of control. You know what? That's great. You should have that level of control, because when you do an FMEA, what should the FMEA do? It should identify all your inputs before you switch the process on. Before a new process starts, you should have identified all the inputs, and from that, what does an FMEA create? It creates a control plan. What should also be happening, of course, is you will have ISO 9000 accreditation maybe, or a TS accreditation, or some other version that has been updated recently. And of course, what should your ISO 9000 be doing? It should be auditing the control plan that controls the inputs that made your CPK do that. And if you do that, these make money. These things all make money. Now, whether you do it with process flow, cause and effect, or whether you're brilliant and you already do it with FMEA, I don't care. But when Six Sigma steps in to fix the capability, and that's what it's designed to do, usually it's because you don't do this well. You are a low fidelity, poorly controlled company. What process flow, cause and effect does is show you how to become high fidelity, great controls, controlling the details, and you can transform any process capability this way with no technical knowledge. Just sit down and find the variables and fix them. One last thing, by the way, before we finish this video, if you don't believe this works, take the Six Sigma challenge. If you ask me to come into your company and solve that problem, if I can't do it, don't pay me. Take the Six Sigma challenge if you don't believe me. Also, if you don't believe me, please leave some comments in the box below. I'd love to debate the situation with you. We're all trying to learn better ways of making processes perform in better ways. So leave some comments in the box below. That would be fantastic. If you want to take the Six Sigma challenge, drop me a line. If you want a video on a different subject, leave some comments in the box below and I'll make a video. Whatever you want to do, I will make a video for you. But if you're trying to transform your process capability, process flow, cause and effect, be high fidelity, control the inputs to the process, transform your process capability and make piles and piles of money.